Welcome to this coding session. In today's video, we'll be tackling a fascinating problem titled Problem number 991, Broken Calculator. Together, we'll explore the problem statement, break it down step by step, and dive into different approaches to solve it. Let's get started. This problem is called Broken Calculator, and the goal is to determine the minimum number of operations needed to transform the number start value into target. You have two operations available. You can either multiply the current number by 2 or subtract 1 from it. The challenge is to figure out the least number of these operations required to make the start value match the target. The input consists of two integers, start value, which is the number you start with, and target, which is the number you want to reach. Both numbers are positive integers, and their values can go up to 10 to the power of 9. The output is a single integer representing the minimum number of operations required to achieve the transformation. Let's take a look at some examples to clarify the problem further. In the first example, the start value is 2 and the target is 3. To get from 2 to 3, you multiply 2 by 2 to get 4, and then subtract 1 to reach 3. This takes 2 operations in total. In the second example, the start value is 5 and the target is 8. The quickest way to reach 8 is to first subtract 1 from 5 to get 4, and then multiply 4 by 2 to get 8. Again, this takes 2 operations. In the third example, the start value is 3 and the target is 10. Here, you multiply 3 by 2 twice to get 6 and then 12, and then subtract 1 to reach 10. This path requires 3 operations in total. These examples illustrate the types of decisions you'll need to make to minimize the number of operations. To solve the problem efficiently, we need to consider the constraints and edge cases. The constraints specify that both start value and target can range from 1 to 10 to the power of 9, which means we need an efficient approach that works well even for very large numbers. As for edge cases, if start value is already equal to target, then no operations are needed, and the answer is simply 0. If start value is greater than target, the only possible way to reach target is by repeatedly subtracting 1, which would take start value target operations. Finally, for large inputs close to the maximum limit, the solution must be optimized to avoid excessive time or memory usage. Taking these factors into account will help ensure the solution works correctly for all scenarios. To tackle the broken calculator problem, we can consider a few different approaches. First, let's discuss the brute force approach. The idea here is to simulate the process starting from the start value and repeatedly applying the two operations, either multiplying by 2 or subtracting 1 until we reach the target. This can be done using recursion or breadth-first search, exploring all possible paths. While this method is straightforward and easy to conceptualize, it quickly becomes computationally expensive. The reason for this is that for large values of target, the number of operations grows exponentially. This results in a time complexity of 2 to the power of n, in the worst case, where n represents the number of operations needed. Additionally, the space complexity is n, due to the recursion stack or the queue used in BFS, making this approach impractical for larger inputs. On the other hand, we have the optimized backward approach. Instead of working from start value to target, we reverse the process. Starting from target, we can perform reverse operations, dividing by 2 if the target is even, or adding 1 if it's odd. These reverse operations allow us to simplify the problem and avoid exploring unnecessary paths. The key idea behind the backward approach lies in observing how values change when multiplied by 2 in the forward direction. While this operation increases the value rapidly, it limits the intermediate values that are reachable. By working backward, we eliminate the need to explore such unreachable paths and instead focus directly on reducing the target to the start value. This process continues until the target becomes less than or equal to the start value. At that point, the remaining difference between start value and target can be accounted for with simple subtraction operations. This approach is highly efficient, with a time complexity of log target. This is because we either divide the target by 2 or subtract 1 at each step, significantly reducing its value. Moreover, the space complexity is 1, as we only use a few variables to track the computation. Another approach worth mentioning is dynamic programming. With DP, we could define an array where each index represents a value, and its value indicates the minimum steps required to reach that index. While this method is more structured, it requires substantial memory and computational effort, especially for larger values of target. Specifically, its time complexity is O, target *2, and its space complexity is O, target, due to the size of the DP table. The optimized backward approach stands out as the most efficient solution for this problem. The key insight is that working backward avoids unnecessary computations and directly reduces the problem size in a logarithmic manner. This makes it both faster and more memory efficient than the brute force or dynamic programming approaches. One of the critical observations is how multiplication by 2 in the forward direction causes exponential growth, creating many unnecessary paths. However, working backward simplifies the problem by focusing on just 2 operations, dividing by 2 when the target is even, and adding 1 to make it even when it's odd. This ensures that each step is optimal and directly contributes to reducing the problem size. The process halts as soon as the target becomes less than or equal to the start value, which prevents any further redundant operations. This efficiency, combined with the simplicity of implementation, makes the backward approach the clear choice for this problem. It effectively balances computational speed and memory usage, avoiding the pitfalls of brute force and dynamic programming methods. When comparing the different approaches, we can identify the trade-offs associated with each. The brute force method is conceptually simple and easy to implement, but it is computationally expensive and becomes impractical for large inputs due to its exponential time complexity. Dynamic programming offers a more structured approach, but it requires significant memory and computational resources, especially for larger values of target. The backward approach, on the other hand, requires a change in perspective by reversing the problem, but it is both efficient and direct. It scales well with input size due to its logarithmic time complexity and constant space usage. In conclusion, the backward approach is the optimal solution for the broken calculator problem. Its combination of efficiency, scalability, and straightforward implementation makes it the best choice among the methods discussed. To solve the broken calculator problem using the brute force approach, we need to focus on simulating the process of transforming the start value into the target using the 2 allowed operations, multiplying by 2 or subtracting 1. The main objective is to determine the minimum number of steps required to accomplish this transformation. First, let's understand these operations. Multiplying by 2 doubles the current value, while subtracting 1 decreases the value by 1. These operations allow us to adjust the current value in ways that bring it closer to the target. The challenge lies in figuring out the optimal sequence of these operations. One way to tackle this is through recursive simulation. Here, we explore all possible transformations step by step. At each step, we decide whether to multiply the current value by 2 or subtract 1. However, we impose a condition to stop the recursion if the current value becomes greater than the target, as further multiplication would only move us farther away. This brute force approach, while straightforward, lays the foundation for a more systematic and efficient method to solve the problem. Now, we can optimize the brute force approach by using breadth-first search, or BFS. Instead of simulating all paths blindly, BFS treats the problem as a graph traversal, where each number is a node and the operations, multiply by 2 and subtract 1, are edges connecting those nodes. By using BFS, we can systematically explore all possible paths level by level, ensuring that the shortest path is found. Here's how it works. We initialize a queue to store the current state, represented as a tuple of the current value and the number of steps taken so far. We begin with the start value and 0 steps. To avoid redundant computations, we also use a set to track visited values. Then, while the queue is not empty, we process each state. If the current value matches the target, we immediately return the step count. If the current value exceeds the target, we skip further operations, as multiplying by 2 would only take us further away. For valid states, we enqueue the results of the 2 operations, doubling the value or subtracting 1 while ensuring they haven't been visited before. If we exhaust the queue without reaching the target, it means no valid transformation exists. This structured approach ensures we find the minimal number of steps efficiently. There are some important insights to keep in mind when applying BFS to this problem. First, BFS inherently guarantees the shortest path because it processes all nodes at the current step level before moving deeper. This means the first time we reach the target, we've found the minimum number of steps required. Additionally, we can prune unnecessary paths to optimize further. For example, there's no need to explore numbers greater than the target, as they'll only move us further away. By using a set to track visited nodes, we prevent revisiting the same states, which eliminates redundant computations and improves efficiency. There are also some key edge cases to consider. If the start value is already equal to the target, the result is 0 steps, as no transformation is needed. If the start value is greater than the target, the only operation that makes sense is decrementation, and the number of steps required is simply the difference between the start value and the target. These insights help refine the algorithm, ensuring it handles all scenarios effectively. Let's take a closer look at the data structures that make this algorithm efficient. The queue is the backbone of the BFS traversal. It stores the current state, which consists of the current value and the step count. The queue ensures that all states at the same step level are processed before moving to the next level, which is what makes BFS optimal for finding the shortest path. Alongside the queue, we use a set to track visited values. This prevents us from revisiting the same states, eliminating redundant computations and avoiding infinite loops. The key operations within this setup are straightforward. When we process a state, we dequeue it from the front of the queue. To simulate the next steps, we enqueue the results of the two possible operations, multiplying by 2 and subtracting 1, but only if those resulting values are valid and haven't been visited before. This ensures that the algorithm only explores meaningful paths while maintaining efficiency. Together, these data structures and operations form the core of the BFS solution. Finally, let's analyze the complexity of the algorithm. The time complexity is determined by the total number of states we explore. In the worst case, we might need to explore all numbers from the start value up to the target. Since BFS ensures each state is visited at most once, the time complexity is O, target. As for space complexity, the queue stores the current states to be processed, and the set tracks visited nodes. Both of these structures grow linearly with the number of states, so the space complexity is also O, target. This makes the BFS approach not only optimal in terms of finding the shortest path but also efficient in terms of resource usage, making it a practical solution for this problem. This implementation solves the broken calculator problem by working backward from the target value to the start value. Instead of simulating operations forward from the start value, which can become inefficient, the algorithm reduces the target value to reach start value with minimal steps. The broken calc function takes two inputs, start value and target. It initializes a counter steps to 0 to keep track of the number of operations. The key idea is to reduce the target value until it becomes less than or equal to the start value. At each step, if the target is even, the algorithm divides it by 2, as this is the reverse of multiplying by 2. If the target is odd, it increments the target by 1 to make it even, which prepares it for having in the next step. Each operation increments the steps counter. When the target becomes less than or equal to the start value, the remaining difference, start value target, is added to steps. This accounts for the number of subtraction operations needed to bring the target up to the start value. This approach is efficient because it avoids unnecessary calculations and directly minimizes the number of operations required. The time complexity is logarithmic in relation to the target value, as each having step reduces the target significantly. The solution is optimal and handles edge cases, such as when the target is already less than or equal to the start value, seamlessly by adding the difference directly to the step count. This is the Java implementation of the broken calculator problem. It mirrors the Python logic by working backwards from the target to the start value, using integer division and modular arithmetic to handle even and odd cases. The main difference lies in Java's explicit type declarations and syntax, such as the use of primitive int types and braces for control structures. The overall logic remains the same, ensuring a concise and efficient solution. To solve this problem, we start with the first example where start value is 2 and target is 3. Initially, steps is set to 0. Since the target is greater than the start value, we enter the while loop. Here, the target is 3, which is odd. When the target is odd, we increment it by 1 to make it even. This changes the target to 4, and we increment the steps counter to 1. Next, since the target is still greater than start value, we stay in the loop. Now, the target is 4, which is even, so we divide it by 2. This reduces the target to 2, and we increment the steps counter again, making it 2. At this point, the target is equal to the start value, so the while loop ends. There's no need to add any further steps since the values are now equal. The total number of steps taken for this example is 2. This demonstrates how we can efficiently work backward from the target to the start value using the defined operations. Now, let's move to the second example where start value is 5 and target is 8. We again initialize steps to 0. Since the target is greater than the start value, we enter the while loop. Here, the target is 8, which is even. When the target is even, we divide it by 2. This reduces the target to 4, and we increment the steps counter to 1. At this point, the target becomes less than the start value, so the while loop ends. With the loop complete, we calculate the difference between the start value and the target. The difference is 5 minus 4, which equals 1. We add this difference to the steps, bringing the total steps to 2. For this example, the output is 2 steps. Moving on to another example, suppose start value is 3 and target is 10. Again, we initialize steps to 0 to begin the process. In this case, the target is 10, which is even. We divide it by 2, reducing the target to 5 and incrementing steps to 1. Since the target is still greater than the start value, we proceed. Now, the target is 5, which is odd. When the target is odd, we increment it by 1 to make it even. This changes the target to 6, and we increment the steps counter to 2. Next, the target is 6, which is even, so we divide it by 2. This reduces the target to 3, and we increment the steps counter again to 3. At this point, the target equals the start value, so the while loop ends. Since the start value and target are now equal, there's no additional difference to handle, and the total steps remain 3. This example highlights the efficiency of working backward by leveraging division and increment operations. The key insights here are that by working from target to start value, we minimize the number of steps. When the target is even, we divide by 2, and when it's odd, we increment it by 1 to make it even. Finally, any remaining difference is resolved with subtraction. This approach ensures we perform the minimum number of operations while taking advantage of faster division where possible. The time complexity of this solution can be understood by analyzing the series of operations performed as we move backward from the target to the start value. The algorithm uses a loop that continues until the target becomes less than or equal to the start value. Within this loop, the key operation is having the target when it is even, which effectively reduces the target logarithmically. This is because repeatedly dividing a number by 2 requires a number of steps proportional to the logarithm of that number. On the other hand, when the target is odd, the algorithm increments it by 1, which is a simple constant time operation. These odd number increments do not significantly change the overall logarithmic behavior since the halving dominates the process. Additionally, outside the loop, there is a single subtraction and addition to calculate the remaining steps, which are constant time operations. Together, this results in the loop running approximately O log target iterations in the worst case. Now, summarizing the overall time complexity, the most significant factor is the logarithmic growth caused by having the target. This ensures that the time complexity is O log target. Even when the target is much larger than the start value, the halving process remains efficient, as it reduces the target in logarithmic steps. Moving to space complexity, this algorithm uses only a small, constant amount of extra space. Variables like steps, start value, and target are all scalars, and no additional data structures are required. Since the space usage does not depend on the size of the input values, the auxiliary space complexity remains O1. Combining these observations, we can conclude that the overall space complexity of the solution is O1, meaning it requires constant memory regardless of input size. To understand why this solution is efficient, let's compare it to a brute force approach. A brute force method would simulate all possible operations starting from the start value and attempt to reach the target by exploring every possible path. This would lead to exponential time complexity, as the number of paths grows exponentially with the difference between the start value and target, resulting in O(2 to the power of n) in the worst case. In contrast, the optimized approach works backward from the target, reducing it logarithmically by halving when it is even and incrementing when it is odd. By focusing only on these efficient operations, the optimized solution achieves a time complexity of O log target, which is exponentially faster than the brute force method. Additionally, the optimized approach uses constant space, O(1), while methods that involve recursion or state tracking would require extra memory. This makes the optimized solution far superior in both time and space efficiency. Now, let's analyze the best and worst cases for this algorithm. In the best case scenario, the target is already less than or equal to the start value. Here, the loop does not execute at all, and the solution simply computes the difference between the two values, resulting in a time complexity of O(1). On the other hand, the worst case scenario occurs when the target is significantly larger than the start value. In this case, multiple iterations of halving and incrementing are required, leading to a time complexity of O log target. To solidify this, we can look at the mathematical proof for the big O complexity. Each halving operation divides the target by 2, meaning the number of iterations corresponds to the logarithm of the target base 2. For instance, if the target is 16, the sequence of halving would be 16 to 8 to 4 to 2 to 1, which takes 4 steps, matching log 2, 16. This logarithmic reduction dominates the process, confirming that the time complexity is O log target. When solving the broken calculator problem, there are several common pitfalls to watch out for. First, neglecting edge cases, like when the start value already equals the target, can lead to unnecessary computations or even errors. It's important to handle these scenarios explicitly. Another issue arises when reversing operations such as dividing the target by 2 or adding 1 in the wrong sequence. Always verify that an operation is valid before applying it. Additionally, naive recursive solutions can get stuck in infinite loops or excessive recursion if proper base cases aren't defined, leading to stack overflow or time limit exceeded errors. Optimizing for constraints is also crucial. For example, always prioritize having the target when feasible, as it reduces the value more quickly. Lastly, remember that not all operations are valid at all times. For instance, having an odd target without subtracting 1 first is impossible and can lead to incorrect results. Being mindful of these mistakes will help you write robust and efficient solutions. Now, let's focus on insights that are especially useful during interviews. Recognizing patterns in the operations is key. For instance, working backward from target to start value often simplifies the problem by narrowing down the choices at each step. Problems that involve minimizing operations frequently lend themselves to greedy algorithms. The goal is to reduce the problem size as quickly as possible. Halving is typically faster than subtracting, so prioritize it when you can. It's also worth discussing the advantages and disadvantages of iterative versus recursive approaches. Iterative methods are often preferred in competitive programming settings as they avoid the risk of stack overflow. For problems with overlapping subproblems, pre-processing or memoization can significantly optimize performance by avoiding redundant computations. Additionally, exploring related problems can deepen your understanding. For example, the 2 keys keyboard problem also focuses on minimizing steps, while Coin Change and Jump Game 2 involve optimization strategies that can be applicable across a variety of contexts. Drawing connections between these problems can make your approach more versatile. Lastly, let's explore some alternative approaches to solving the problem. The greedy reverse approach is one of the most efficient strategies, where you start from the target and work backward to the start value by reversing the operations, dividing by 2 or adding 1 as appropriate. While this method is fast, it requires careful handling of edge cases to avoid errors. Another option is dynamic programming, where you use a DP table to track the minimum operations needed for each intermediate value. Although this guarantees correctness, it can be memory intensive. Breadth First Search, or BFS, is another viable technique. Here, you treat each number as a state and systematically explore all paths to the target. This guarantees the shortest path but may be slower for larger values of target due to the high branching factor. Finally, recursive solutions combined with memoization can optimize performance by storing results of repeated computations. However, even with memoization, recursion might still encounter Stack Overflow for very large inputs. Each of these approaches has its pros and cons, so the best choice depends on the specific constraints and requirements of the problem. Great job! We've summarized the key insights from today's problem-solving session. Remember, reverse thinking and optimization are powerful tools in algorithm design. If you enjoyed this video, make sure to like, share, and subscribe for more content like this. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!